Welcome to Hot Chips 2023. Session 7, ML-Inference.
All right, welcome everyone. I'm Grant Ayers from Google. I am the chair for session 7, ML-Inference. In this session we have 4 presentations, one each from IBM, Moffet AI, Qualcomm, and Numenta. If you haven't yet done so, please join the session 7 Slack channels where you can discuss each of the talks as well as add and vote on questions which will be read during the Q&A. Also, please lower your metabolism to reduce the heat in the room. Well, maybe don't do that if it puts you to sleep. But let's get started. And our first talk today is the IBM NorthPole Neural Inference Machine presented by Dharmendra Modha. Dr. Modha is an IBM fellow and pioneer in brain-inspired computing. Author of over 80 papers and inventor of over 200 patents, Dr. Modha has received ACM's Gordon Bell Prize, Usenic's Fast Test of Time Award, several Best Paper Awards, and was named R&D Magazine's 2016 Scientist of the Year. He is a fellow of IEEE and a distinguished alumni of IIT Bombay and the UCSD ECE department. Dr. Modha's previous work, True North, was commended by President Obama and has been accepted into the Computer History Museum. It's all yours.
Thank you, Grant. Good afternoon. In my hand, I hold NorthPole, 22 billion transistors, fully functional in first silicon. Thank you. Very rarely you can see that. And of course, this is the work of an extremely talented group of people. I'll talk about a lot of metrics today, but in the metric of frames per number of people, our team leads the world. So why NorthPole? As we heard, the OpEx and CapEx of AI are becoming unsustainable. So let's look at energy and space efficiency in a precise mathematical fashion. So on the x-axis is energy efficiency. So given a joule of energy, how many frames can be classified? On the y-axis is capex, which is, or inverse of capex, which is given a transistor, given a second, how many frames can be classified? Now here are 3 CPUs. The numbers are found from various papers, respective parties, third parties, and are available upon request. Going from CPUs to GPUs from 2 different parties, you can see a wide spectrum. And finally, going to various accelerators. Putting them all together, this is the picture. Now to see NorthPole, we'll take the exact same data, but we'll extend the x and the y-axis, leading to this picture. And here's NorthPole. So you can see NorthPole is many factors greater in terms of energy and space efficiency. what is striking is that the leading contemporary architecture is at 4 nanometer. NorthPole is a 12 nanometer node. Compared to a 12 nanometer GPU, NorthPole is 2,500% higher energy efficiency. So this brings to mind two thoughts. One is that architecture trumps Moore's law. And second is that there is significant room for silicon scaling for NorthPole. Now, this is the same result for YOLO v4 detection network. Same axis. And this is one more result for a large language model, one of the smaller ones called BERT base. Again, a very similar result. So now let's turn from energy and space to time, which is latency. Latency is the speed of response. What you see here on x-axis is latency in log scale. The axis is inverted, so lower latency is to the right. Y-axis is throughput. And here are all the numbers. You can see TSP to the right has very low latency, but as we saw in the previous chart, NorthPole has significantly greater energy and space efficiency. With respect to other architectures, NorthPole is plotted for a series of batch sizes, n equal to 1, 2, 4, 8, 32. And you can see that at every latency, NorthPole has higher throughput, and at every throughput, NorthPole has lower latency. In other words, NorthPole provides a throughput latency frontier. Same result for YOLO v4. So, how did we get here? How did we achieve this technological feat? The story goes back to July 16th, 2004, when I had a stark realization that I was going to die. Well, not imminently, but eventually, like all of us. And so I decided to focus my life's limited energy on problems that matter, in particular on unlocking the puzzle of brain-inspired computing. And that resolution brought together a series of extremely talented colleagues, and rest has been a very fast race. We carried out simulations at the scale of mouse, rat, cat, monkey, human, winning the ACM Golden Bell Prize. We mapped out the largest wiring diagram in the primate brain. We created 2 tiny chips at the scale of worm brain, 256 neurons. And then we created True North, which is 4,000x the 256 neuron with 1 million neurons. True North won a Misha Mahowal Prize, is in the Computer History Museum, and was recognized by President Obama. And then, from 2018, nothing. Reality is, it was a beehive of activity. And that's how we are here today. So let's take a little bit peek under the hood at the NorthPole architecture. So the NorthPole is a core-based architecture, where cores are tiled in 2 dimensions. So let's begin by looking within one core. So inside the core, the center of the core is a vector matrix multiplier. The VMM is capable of 8-bit, 4-bit, and 2-bit precision. It can do 2048, 4096, 8192 ops per cycle. It can support mixed precision, so write precision can be selected for every layer. The output of VMM feeds into a vector compute unit, the output of which feeds into an activation unit. The entire operation is fully pipelined to allow for high utilization. Now, we heard over and over that one of the primary causes of energy is moving data. So in NorthPole, Memory is closely coupled with compute within few microns. So VMM, vector unit, both have private memories. On the core, there is 768 kilobyte of unified memory for storing weights, programs, and neural activations. Now, coupled with the compute and the memory is a control. It's a very unique form of control. There are 8 threads per core. There is no VLIW instruction way of programming that. Each thread is independent, but synchronized by construction. The entire operation is fully pre-scheduled. So it's completely deterministic, predictable, verifiable. And the way this is achieved is there is no data-dependent conditional branching. So this breaks path with Turing's original idea of if then else. There are no cache misses. There are no stalls. There is no speculative execution. Now, if you look at the layout, Tom, of the core, then you can see that not only memory is near compute, they are intertwined. The red is compute, the blue is memory, and you can't tell one apart from the other. And that's the secret to low energy. So now, memory is close to compute, and it's a distributed core architecture. But the disadvantage, or so it would seem, is that memory is now fragmented. So memory is distributed. So to unify this otherwise fragmented memory, we introduce 4 networks on chip. 2 networks are inspired by the cerebral cortex, and 2 networks are invented to optimize for silicon. So the first 2 networks, activation network on chip and the partial sum network on chip, are inspired respectively by the long distance white matter pathways in the brain and the short distance gray matter pathways in the brain. And the silicon optimized networks on chip, model network on chip used for moving weights around between cores, and instruction network on chip used for moving programs around between the chip. And these networks enable on-the-fly reconfigurability. This is very important because brain architecture is implemented in a technology that is optimized for 10 hertz. And today's silicon can run at 5 gigahertz. So there's a huge speed disparity, and implementing brain-inspired architecture on silicon as such leads to very low capital efficiency. So now, the 4 networks on chip together constitute 4,096 wires crisscrossing each core in both dimensions. A total of 64,000 wires. And now that we have the core, the cerebral cortex famously is modular. And so our architecture simply consists of tiling the core array in 2 dimensions. And that's what's shown on the upper right. And then once you have this architecture, in a 12 nanometer silicon implementation, this is how the 2 by 2 core array looks. NorthPole has a 16 by 16 array of cores with massive parallelism. Distributed among the cores is 192 megabyte of memory for activations, models, programs. Sitting between the chip and the outside world is a 32 megabyte frame buffer for input-output tensors. It serves as a staging area. As I mentioned, 800 square millimeters area, 22 billion transistors, fully functional in first silicon. No MPW, no other tape out. So NorthPole is a very unique architecture. Compute is red, memory is blue, squint your eye, To the left, you see a GPU, TPU, CPU. What you see is centralized memory. What's not shown is off-chip memory. NorthPole has no centralized memory, no off-chip memory, has no von Neumann bottleneck. Now, many of the typical accelerators today are really layer accelerators. So given a hypothetical 3-layer network, each layer is loaded onto the accelerator, loaded out to the off-chip memory or to the cache. So there are 6 interactions, and that's what you'll see to the left. NorthPole, however, is a network computer. The entire network is loaded on the chip. All one does is write a tensor into the network, into the chip, and after a little while, out comes another tensor. So NorthPole has the simplest possible I/O model. Write tensor, run, get tensor. It is essentially an active memory. It just looks like a memory, works like a memory, but I would argue is compute. Entire network is on chip, and therefore minimum load on the host, minimum possible I/O bandwidth. And now, as I mentioned, the VMM has 8, 4, and 2 bits of precision, and we have been pioneering methods to achieve state-of-the-art accuracy with mixed precision. In particular, we have developed 2 algorithms for quantization-aware training called FAQ and LSQ, and we have also developed 2 very innovative techniques for selecting the right precision for each layer. The key message I want to leave you here in the interest of time is low precision does not equate with low fidelity. Now, NorthPole is capable of implementing a growing list of networks. So what you see here on the x-axis is the parameter memory, the memory required to store the entire network on chip that goes up to 128 megabyte in log scale. On the y-axis is activation memory, which is the size of the largest or the widest layer as you're computing, and that also goes up to 128. Now remember, I told you each core has 768 kilobyte of memory. There are 256 cores, so 192 megabytes. Therefore, the sum of these two must be 192 megabytes. Within these constraints, NorthPole is capable of implementing a wide variety of networks for classification, shown in blue. For detection, for segmentation, for video classification, for speech recognition, and for language models, transformers. Now, this configuration is ideal for a single NorthPole chip. What if the parameter memory exceeds? Well, then scale out is a viable approach. What you see here on the y-axis is the exact same activation memory going up to 128 megabyte of memory. And on the x-axis is number of NorthPole chips, going from 1, 2, all the way to 16. And this is a list of networks that can be implemented. This list will continue to grow with time as we add more and more layer primitives to our library. And to the very right, to the top, you see an example networks, which is Llama 2, 7 billion parameter model with 2-bit precision, would fit in a 16-chip configuration. Now, NorthPole has an end-to-end tool chain. So the entire tool chain is containerized and supports the standard train flow along with the precision, mixed precision training, as well as a run flow. And the run flow, as I mentioned, is extremely simple, imposing minimum load on the host suitable for autonomous operation. And NorthPole systems. So NorthPole is currently packaged in a PCIe card. So on this card, you see NorthPole, you see FPGA. FPGA is only used as a bridge for PCIe. Most of the FPGA is completely empty. It performs no processing. In a future version, we'll just move the PCI IP on chip, and there will be no FPGA. You can observe that on this board, there is no high bandwidth memory, there is no external memory, there are no CPU cores. And this board just simply serves 3 commands. Write a tensor, run a network, read a tensor, again active memory. Therefore, the entire board can be Ethernet enabled like a little node answering queries. Now this is the full NorthPole assembly along with a heatsink and various other supporting casts. We over optimized for heatsink. In future it will be much thinner. And this is an example NorthPole system that we have running in our lab. It's a 1U server with a single NorthPole assembly. And going beyond, we have running a server, 1U server with 4 NorthPole assemblies. And it's possible to create easily servers with 8, 10, 12, or even 16 assemblies per server, with of course larger bits. Now observe that each of these assemblies could be running a separate model, or each of these assemblies could be running one model. So when you have a large model that is striped across each of the 4 boards. So this offers a very simple scale out. Scale out increases frames per second, increases the total available parameter memory, but it keeps the energy, space, and time efficiencies. It only has very low bandwidth data tensor moving between the assemblies via PCIe, so no need for extremely high speed optical and other technologies. So with that, let me bring this presentation to close. I thank you, and I would like to say this is a very important moment. To this date, brain-inspired computing has been a promise. But today, based on the numbers that you saw, brain-inspired computing is old enough and is bold enough to make its foray into the world. Thank you.
Thank you, Dharmendra. For questions, please line up at either of the 2 microphones, and also please state your name and affiliation before your question. And let's begin with Slack.
Can you hear me? Okay. This question was posted by Tom St. John from OctoML, but it got a lot of upvotes from other people as well. Do you have any plans to submit to ML-Perf inference to validate your performance energy efficiency claims?
Yeah, that is on our list of things to do.
I think everybody would be eager to see the results. So.
Okay, let's go house right over here.
Hi, thank you for the talk. A question you mentioned for a larger model like Llama 7 billion, you require to run. For larger models like Llama 7 billion, you run them model parallel across multiple chips. Did I get it correct that those different processors cores talk to each other via PCIe? And if bandwidth is enough to do model parallel, can you comment on performance, like what latency and throughput you see with 7 billion model?
So that's the whole beauty, right? So as long as the entire network is cut up such that intersection bandwidth is less than PCIe, which for most networks it is, as I displayed the list of networks, and the tensor size that is traveling fits within the frame buffer size, we are just able to, there is no latency disadvantage, and you keep the energy and the space efficiency.
Do you have any latency or throughput numbers for 7 billion model running on a chip?
Oh no, this is, so far, all of our experiments have been on a single chip, and now we are looking forward to going forward. So this is, this is the direction that we are going to go next.
Oh, okay, you just mentioned that. Sorry, got it, thank you.
Thanks, Natalia.
Okay, thank you. House left over here.
Thank you. Nathan Brookwood from Insight 64. Fantastic presentation. I really enjoyed it. But you showed pictures of NorthPole with the lid on. If we pull that lid off, what are we going to see? Is it a monolithic piece of silicon? Is it chiplets? How is it physically implemented?
So I see that you have a press pass. So unfortunately, I am not able to talk to the press today in any form.
Talk to them.
But
Just take the badge off and re-ask your question.
But seriously, what's going on under the hood? And also, how much power does that chip consume?
I think the same answer.
Oh, come on, that's lame.
Okay, let's move on. Let's go to Slack again.
Okay, this question is from Christoph Novak. Were all those models actually tested on your prototype silicon, or were those simulation results?
Can you repeat the question?
Certainly. You posted results for a large number of models, supposedly running...
Those are measured numbers on actual silicon.
That was the question, thank you.
Okay, over here.
Dr. Modha, fantastic talk. Michael Ari from NASA. Quick question. All the evidence from neuroscience is that learning, or I should say synaptic modification, is intertwined with processing. And what you're presenting here in the ML-Inference is inference only. Are there any aspirations to incorporate synaptic modification in the processing flow of NorthPole?
With a couple $1 billion and 10 years roadmap, I'll be happy to entertain your request.
Along the same answers as for the press. Thank you.
Okay, let's thank our speaker.
Thank you.
All right, our next talk is Moffet Anthem, a Deep-Sparse AI inference system on chip for vision and large language models, presented by Zhibin Xiao. Dr. Xiao has over a decade of hardware-software co-design experience in developing CPU, DSP, and hardware accelerators, including video codecs, databases, and machine learning. Currently, Dr. Xiao is the co-founder and chief architect of Moffet AI, where he leads the development of sparse AI accelerators and systems for data center applications. Previously, he was a founding team member of Alibaba Cloud Chip Business Unit and worked in AI chip and ARM CPU projects as a chip architect. Before Alibaba, he worked in Oracle as a principal engineer in the software and silicon team, building several generations of in-memory database accelerators. Dr. Xiao received his PhD in computer engineering from the University of California, Davis in 2012. The floor is yours.
Thank you. Thank you, Grant, for a very nice introduction. My name is Zhibin Xiao, and today I'm going to introduce the Moffet Anthem, which is a deep-sparse AI inference chip for vision and language models. So this is an outline of my talk. In case you missed my tutorial on Sunday, so I will give another update on the introduction to machine learning chains and the sparsity in inference. And also later I will introduce the Anthem microarchitecture and the application software stack, as well as the final some of the performance results in ML-Perf. So this is one of my favorite image on the brief history of AI models. As we all know, the outbreak of the modern machine learning outbreak starts from 2012 AlexNet, and actually divides into two phases, from 2012 to 2018, and this is the outbreak of the computer vision models. And from 2018 to 2023 until now, it's an outbreak of transformer-based GPT kind of application. So as we can see in this graph, as we can see here, so there's two chains for the AI models. The first chain is the model architecture is become limited to a small subset, and the operation of those AI models is also become very limited. So it's basically a convolution, matrix multiplication, transformer-based architecture. And the second chain of AI models is that the data, the training data size increase dramatically, and the model size also increase dramatically. So considering these two chains, let's look into a little bit deeper into the characteristics of computer vision and language models. So when we started this Anthem project in 2020, so we think about at that time BERT is popular but not that popular. We think about to design this chip to support both computer vision and the language models. So for the computer vision kind of models, they have some very unique characteristics. So the model is normally very small, considering the gigantic large language model we have right now. So the model size is normally millions of parameters, and the input size is very huge. It normally takes 1080p, 4K, even 8K images. And the vision models is also a throughput sensitive application under some certain latency constraint. And also to support computer vision applications, there's a lot of non-AI functions such as image processing, video codec, and pre and post processing kind of tasks. And in general, the computer vision models is more computational intensive and is more computation bounded. Compared to the computer vision models, the large language model or the language model has different workload characteristics. So normally the model is large, has billions of parameters, and the input is normally very small. For example, for the GPT kind of architecture, they normally takes 128 to 32K context window, and it's both latency and throughput sensitive. And also the large language model is data dependent. For ChatGPT kind of application, is decode token by token, so it's a data dependent, very data dependent application. And also there's a change. The inference, we used to use one single card for inference, but to support large language model, we are scaling out to use multiple cards to support AI inference. So, and in general, those large language model is memory bounded or IO bounded problems. So at that time, we think about sparsity can solve both issues. It can reduce the memory bandwidth and capacity requirement, and also can reduce computation time. So sparsity is one very unique feature we want to support in our chip, so we can support both vision and language model. So this slide gives you an overview of the Anthem architecture. It's a Deep-Sparse domain-specific architecture. So it targets vision applications and also the AI-GC applications, including stable diffusion and also the large language models. And also there's some specific new features, including it has very efficient bank balance structure sparsity support. So it can support up to 32x sparsity. And also it has a programmable vector processing unit which has a very large vector size. And it's a near memory architecture, so of course it has a lot of on-chip SRAM, up to 82 megabytes of on-chip SRAM. And it's a full SoC with a lot of other accelerators, including video codec, image processing. And we also have quad-core ARM CPU that can run Linux. Okay, next I will introduce a little bit more on the sparsity in machine learning inference. So as we all know, the core of the machine learning inference is a tensor algebra. So it's basically it's a matrix multiplications with different dimensions of tensors. So the sparsity actually is a very natural feature because zero naturally exists in the tensors, and also zeros can be induced in the tensors. It has huge benefits, as I mentioned before. So it can reduce the memory bandwidth, capacity, and reduce power, and also have real world clock time speed up. But this comes, all of these benefits comes at a cost. We call this a sparsity tax. So you need extra memory or storage to store the index or store different metadata for the compression, the weight matrix or activation matrix. Also, you need some hardware to do the compress and decompression, and also you have to make sure there should no workload imbalance problems to make every processing element can be utilized. They cannot sit idle there when there's the model is imbalanced. So there's different types of machine sparsity. So we all know about sparsity, but normally people know this is just weight sparsity. But there's different, there's different kind of sparsity. So there's a static sparsity. So you prune the model before long time, you have a sparse model, and then during the long time, the model is not changed. And there's a dynamic sparsity because there's an input feature map or input context window, context sequence is there's a sparsity in the input data, and also there's a conditional sparsity, which is really new. So conditional sparsity is very important for the large language model because the large language model, the computation cost, the memory, KV cache kind of storage is quadratic with the input sequence. So there's a lot of active research on the contextual or attention sparsity, or there's like Jeff mentioned in the keynote, there's a pathway kind of a mixture of expert sparsity. And in terms of granularity and the structure of the sparsity, there's a coarse-grained sparsity, and there's also a fine-grained sparsity. So Moffet actually support a hybrid of this kind, all this sparsity format. It support bank balanced structure sparsity, and also can use a hardware software hybrid approach to support MOE kind of or attention based sparsity. I will introduce a little bit later. So in order to design such a very complex SoC with sparsity, because the sparsity you need to think about accuracy and the sparsity tax, we develop a very comprehensive end-to-end compile-aware architectural simulator for AI accelerator design space exploration. So as we can see here, this simulator actually is divided into 4 parts. So there's architecture definition. So you define your hardware architecture, and it's divided into different components. And you have a workload definition, and this workload, actually this part can take any Onyx model as an input. And also we have we put the compiler path into the architecture simulator. So we do a lot of like memory allocations and operation scheduling and dead code elimination and constant folding, something like that, and operation fusion in the compilation part. So this architecture simulator has a GUI interface. It can run some model with very fast, so we can explore the different design architectural kind of options before we even have the RTL or C model. So next, I'm going to give a little bit more detail on the Anthem microarchitecture. So Anthem is SoC. So it has 4 NN core. We call this NN core subsystem. So we have 4 NN core subsystem, and it supports PCIe Gen 3 by 16 and LPDDR4X. So this with sparsity. That's why we choose. We don't have to use very high-speed external interface, inside each of the NN core subsystem, there's 8 different sparse processing units, and there's one very large vector length vector processing. In the previous slides, we discussed about machine sparsity type and different machine learning inference chains, and we designed this Anthem chip to support very deep sparsity. So this is an core. This is a SoC chip that can run Linux, and it has 4 core subsystem, and inside each subsystem it has 8 sparse processing units, and also it supports very large vector length vector processing unit. It has many domain-specific accelerators for maximum efficiency, and also it is it has a multi-level memory hierarchy for maximum memory efficiencies. And it also has accelerators for multimedia and image processing. So next, I'm going to introduce one of the most important features for our Anthem chip. It is the sparse processing unit. So this unit actually is designed 3 years ago, and actually is before the announcement of NVIDIA's 2.4 kind of structure sparsity. So we design a very deep sparse like a processing unit that support NM kind of bank balanced structure sparsity, because we think structure sparsity is the way to go, that it can avoid many problems of workload imbalance. So the sparsity ratio for this unit can support from no sparsity to 32 times of compression ratio, and also the bank size is 16, 32, and 64. And the unit support both precision int8 and BF16 format. And as we all know, this is a programmable architecture, so the bank size, the compression ratio, and also the precision can be programmable through commands or instructions. And also these units, as we can see here, so inside each of the matrix, sparse matrix, you can divide into multiple domains, multiple small matrices, and these small matrices can be mapped to a single command or single instruction. And inside that single instructions, and then the compression ratio, the bank size, and also the precision can be different. So this offers much more flexibility to the algorithm designer to design their to compress the model, so they can increase the accuracy of their model after pruning. And also this unit supports native convolution, deconvolution, depth-wise convolution kind of matrix replication operations. And it supports, also it can support dense model without extra overhead for storing the index for the sparse format. We also have the N-core subsystem is composed of a SPU cluster. So this figure shows a pipeline of the SPU clusters. So as we can see here, there are 8 SPUs, and each SPU has an 8 by 9 kind of processing array, and each processing array has 8 hybrid MAC, support both integer 8 and BF16, and it has a 20.5 megabytes of weight buffer and a global buffer which can be shared among wait and activation. And it has separate L1 cache or L1 cache for the wait and for the activations in the around like 288 kilobytes for the L1 wait buffer and 320 kilobytes for the activation buffer. So in this pipeline, as we can see here, there's a shuffle network that can fetch the data from the global buffer and to arrange the data in the format that the SPU array can take. And then there's also some fusion unit can fuse some of the operations like batch normalizations and element-wise operation element-wise operations, quantizations, so on and so forth. Yeah. So after we optimized the convolution and the matrix applications, we found that there's some other operations that cannot be specified, and that will become the bottleneck. That's why we designed this very large vector length vector processing unit. We designed this vector processing unit. So it has 512 lanes of element wise. It can support 512 elements kind of operations. And it is highly programmable. So we use this unit for implement functions like pooling, average, mean, and element-wise operations. And also it can support int8 and BF16 format. So this is a very traditional vector processing unit. So it has a 32-bit instructions, encoded instruction. It has 15 plus kind of instructions. It has two types of instruction. First is the list-like instructions. So those instructions operate on the vector registers, and there's a sys-like instructions. Those instructions actually operate on the global buffer and constant buffer, so then they can directly stream in data from global buffer and then directly stream data back to the global buffer. So there's also a shuffle network for gathering or the mask on mask shift of data read from global buffer to global buffer. So other than the SPU and VPU, we also design several very domain-specific accelerators. This including activation engine, the transport engine for memory reshape operations, and the top K engine. So the activation engine, we actually use a polynomial approximation of 10 different activation functions, including like softmax, exponential, and Jaloo. And then using these basic operators, we can combine this to make some more complex functions, mass functions. And we also support a transport engine that can swap the dimension to transpose the different dimensions of the tensor. And we have also implement a top K engine that's for for example, for the beam search or some of the NMS function in the fast RCCN network. So it can iterate sorting algorithms that can support to select the top K numbers out of a large number of n. So to connect the full N-core subsystem, we design a core-to-core interconnection network. So it is a unidirectional ring interconnection with bandwidth 115.2 gigabyte per second. So the NOC interface supports very simple programmable primitives, including send, receive, and sinks. So in the thread of each NN core, they can have a send-receive command to utilize the interconnections to share weight among cores or send activation feature map to different cores. So there's several typical use cases for this interconnection network, including because we compress the model. Most of the time, the model for vision models, we can put the whole model on the on-chip SRAM. So, but sometimes it's too large. Then each core can hold a piece of the weight. So we can use these core-to-core interconnections to shuffle the weight, rotate the weight after the one core finished use its piece of a weight. And then this N-core interconnection network can support data parallelism and model parallelism kind of partitioning among these cores. So before I conclude the microarchitecture session, and I want to emphasize how we support the sparsity or accelerate LLM on Anthem. So active sparse LLM is a very active research area. As we mentioned before, there's activation sparsity, contextual sparsity, attention sparsity, and MOE kind of coarse-grained sparsity. So we use a very hybrid kind of sparsification approach. So at the so all inside the LLM models, all these weight matrix, including the KQA weight matrices, and also the 2 layers of feed-forward layer network. So the matrix, the weight matrix can be pruned before runtime using bank-balanced sparsity, structure sparsity pattern. And after that, we have some scheduler and CPU that can use some of the accelerator to calculate the conditions. So they can the CPU or the scheduler can use the conditions, dynamic calculate conditions to schedule which part of the network to activate. So, so this is actually, that's why our chips support both activation sparsity and fine-grained bank balance structured weight sparsity, and also coarse-grained like sub-module level of coarse-grained sparsity. So this is an implementation result of this Anthem chip. So it is implement using TSMC 12 nanometer CMOS technology. The die size is 340 millimeters square. It typically runs at 800 megahertz. So the dense tops is around 30 tops for int 8 for single chip, and it supports both BF16 and int 8 precision. And it uses a PCI Gen 3 interface and LPDDR5X, LPDDR4X memory interface. One single chip supports 20 gigabyte LPDDR4X memory. So it also supports the very high throughput video codec and image JPEG decoding kind of capability. So the TDP of this single chip is 70 watts. The actual chip power is much lower than this. So this is the PC, the chip, the S4 single chip card power. So based on one chip, we designed 3 different PCIe products. So we have a single chip S4 cards and dual chip S10 cards and triple chip S30 cards. So the performance and memory capacity is scaled very linearly, and the power is 70 watts, 150 watts, and 250 watts. And next, I'm going to introduce the software toolchain and the application performance. So as we all know, there's no difference compared to the other AI accelerators. The only difference is we add a SDK library called Sparse OPT, which can do the optimization of the models for the pruning and the quantization part. So this figure shows very simple steps for this. How do we do the software toolchain workflow? So the only difference compared to the normal flow is this compression part. So let's jump to the result. So this is actually very interesting result. So we prune the Resonant 50 and BERT models under different compression ratio, and then we get different throughput. The 2 figures in the above, we can say that from 1 to 16 times of compression ratio, the throughput or speed up of our of the application performance is linearly scaled in our chip. For both Resonant 50 and BERT model. And in the bottom is accuracy versus throughput. So this is an insight I want to emphasize, is that we also, for example, for Resonant 50, we also prune a Resonant 152 models. And for BERT, we prune both the BERT base and BERT large. As we can see here, so if you want to achieve the same kind of throughput, so you can use a larger model, so you can get a better performance using Resonant 152 here, from here to here. And if you want the same accuracy, then you can still use we can still use the same model, but you can have higher throughput. So basically, sparsity can give you both throughput and accuracy. And for the BERT base and BERT model, the story is the same. And this is a publishing a paper you can see later we published a paper in the Sparse workshop. We mapped the result. We mapped 176 billion Bloom models to 8 S30 cards, and I'm not going to go to the details of the mapping, but it's basically used the model parallelism, data parallelism, as mentioned in Beer's talk. But it is for inference, not for training. So this gives some results on the latency on different batch size for Bloom model with different context lengths. And the latency as in a typical 2K kind of context window of the batch size 1 latency is around 21.4 milliseconds. And for the batch size equal to 2 is around 64 milliseconds. So I think some of the people ask about the ML performance. Actually, we submit results for multiple rounds of ML-Perf. But the sparsity is not allowed in the closed loop, so we submit to the open division. So we have submit results for last year and this year, and also this year we also have some results to be announced for the GPT-J 6 billion models. So as we can see here, the performance is for S30 is around over 90,000 images per second for the ResNet 50 models, and for the BERT large, it is over like 3,800. Okay, so I think I have limited time, so I have to wrap that up. So this is a ML-Perf result. And then there's a very simple demo. It shows the sparse super resolution on S4 card. As we can, I will skip the data set and model, but it's an archive model which do increase the model from 360p to 720p. As we can see here, with around 8 times sparsity, we can achieve close to 7 times of speed up. And the result is almost the same as the original one with the sparsity one. So this is the original very blurry picture, and then there's 2 pictures. This is the original model, and this is a compressed model. You cannot tell the difference. And there's multiple more images here. Okay, that concludes my talk. And we introduce Anthem SoC chip, which supports deep sparsity. It's a domain-specific architecture. It has multiple efficient accelerators. And also we propose end-to-end compile-aware architecture simulator. And we achieve very good result on ML-Perf. And thank you. That's it.
All right, so in the interest of time and with that power disruption, if it's okay with you, can we take your questions on Slack?
Yeah,
okay.
Sure, no problem.
All right, thank you so much. Let's take our speaker again.
Thanks, Gabriel.
All right, our next talk is Qualcomm Hexagon NPU, presented by Eric Mahurin. Eric is a Senior Director of Technology at Qualcomm Technologies. His passions are computer arithmetic and parallel computer architecture. At Qualcomm, Eric created and led the development of 2 SIMD extensions that are in billions of devices. Prior to that, Eric worked across disciplines in microarchitecture components and CPU development for AMD, Intel, and Oracle. Mid-career, he broadened his experience at several startups working on compute-intensive EDA software algorithms. Eric received his MSc in 1993 from Wright State University. He holds over 80 US patents. It's all yours, Eric.
Hey, thank you, Grant, for the intro. My name's Eric Mahurin from Qualcomm, here to talk about the Hexagon NPU. So 8 years ago, we came to Hot Chips, and we introduced Hexagon with vector extensions. We targeted those extensions toward image processing, but we ended up applying it to all kinds of things, and eventually it became a really good deep neural networks inference engine. Today I'm going to talk about Hexagon NPU. It's our next leap, yielding new levels of performance at low power across a new diverse set of use cases. I'm going to talk about what this NPU is and about some of our design choices. And you might see some differences about what you've seen elsewhere today. So first I'm going to talk about the hardware. So Hexagon NPU has 3 types of instructions in it, or 3 types of processors or processing in it. There's a scalar side. This is CPU-like. It has a 8 wide, it effectively has an 8 wide superscalar in it, like a high performance CPU would. And is used for control flow, serial data processing, and it was introduced also, I think about 10 years ago, and then talked about it again 8 years ago as well. And then vector. So this is what we introduced 8 years ago. And it's used for general purpose data parallel compute. And it can do pretty much the same things as scalars can do when there's a data parallel workload. The performance will be roughly 30 times or higher performance in the vector than the scalar. Tensor. So this side, again, it's a much higher performance than the vector. This one focuses on matrix multiplying and convolutional layer. Not general purpose like the vector, but when the workloads fit, more than an order of magnitude higher performance. Probably about 30 times as well. So it's a big scale from the scalar vector tensor going up there. And this is over multiple threads. On the 8 Gen 2, Snapdragon 8 Gen 2, it's 6 threads in this core. And this is all over, all those communicating over shared memory, both cached and tightly coupled memory here. So the roots of Hexagon NPU are DSP. We have VLIW, hardware looping, target all kinds of DSP type workloads, compute math heavy things like that. But also a bunch of CPU like features. You might as well call this a CPU because virtual physical, address translation, security, lots of caching levels, branching, exceptions, interrupts, all those things. And if you have some software that is CPU agnostic, it'll compile on this. We've had Linux and such running on this, all the compilers, so it's as general purpose as a CPU. So our strategy here has been, unlike some of the other approaches, our strategy is really to maximize what we get out of a single core. So we do try to maximize squeezing as much out of each core as we can, getting in terms of all the compute resources, the memory resources. So first I'll talk about the vector extension. So our vector extension, again, we introduced it 8 years ago, and back then it was 1024-bit or 1 kilobit SIMD, 128 byte, not 128-bit. That's what it was back then. Was still well, actually back then I think we introduced it as 64 byte. And we could pair it together to be 128 byte, but we've been using 128 byte for the most part across all the parallel workloads. Initially, our focus was fixed point, really on byte. Byte was our big deal, but now we also support floating point. So just to give a little view of our compute resources. There's a four-way. It's kind of like a four-way superscalar. It's VLIW though, in terms of the compute resources. 32 vector registers, kind of pretty standard, and we have some predicate registers go along with this. And in the 8 Gen 2, we had 4 of these types of engines in one core. able to execute 2 of these fully pipelined per cycle. So there'd be 2048 bits of throughput across all of these compute resources in parallel. And that was in that one core. And memory access, we have, obviously loads and stores, but those can go to, for the vector engine, both cacheable memory and the TCM. And then we have somewhat new is a scatter gather, so it's fully parallel, but that only goes to our TCM, and it's because we wanted to make it very, very high performance. So the target applications, originally, like I said, it was for image processing, but eventually we moved on to DNNs, and it was before we knew about kind of what a DNN was. This thing worked pretty well, and we had a lot of the instructions that I've seen in some of the other SIMD architectures way back then. But like the 4-way multiply add on the bytes, for example. That's because our focus really was image processing, and it was bytes. It ended up being a really great thing for DNN right out of the gate. So that was what I just talked about. It's pretty much a lot of performance, but we treat those as our little guys. So these are our big guns. This is our Tensor engine. So it's also SIMD, but it's Tensor SIMD. So instead of the quantum being a vector, it's a tensor. Has lots of dimensions, and that's our parallel quantum that we work with, one tensor at a time, a hardware tensor that fits into this SIMD architecture. So bit widths, we focus on integer, 8 and 16 bit for both activations and weights, and then we also support 4-bit on the weight side. And then the floating point, FP16, for both activations and weights. So this ISA, like I said before, it focuses on matrix multiply and convolutional layer. And also, we also accelerate the depthwise and small group convolutions. Not at full performance, but we execute it in this engine here. And then, so we take the memory here on this accelerator, and it basically multiplies the weights times activations to get into the accumulator, and then on the way back, we have instructions that would take those results, down convert them back into memory for the next layer. And then along the way, some fuse activation functions. We use polynomials to do the activation functions, basically fit whatever activation function you want, find some coefficients that fit to that activation with a little bit of clipping and such. And then for really handling the low precision, the 8 bits, 4 bits, we have per channel scaling. That's basically what that does is it creates kind of a block floating point format per output channel. So each output channel, all integers, but you get to have a scale with each one. It's like an exponent. So next I'll talk about the programming model. So in Hexagon NPU, it's basically a bunch of the core is really just a bunch of threads, a bunch of programs, and just like a CPU. So each thread has its own program. They're all executing just like you would in a CPU. The scalar ISA used for normal scalar compute. They can communicate with each other, and just like a normal CPU. So then we have our SIMD extensions. Our SIMD extensions are a little different. part of the instruction set, but they're treated as a shared resource. So it's not every thread gets these instructions. The thread effectively acquires a resource to use these, and then they can execute and have these capabilities. I also like to say something else that's a little different about the SIMD extensions, in that they don't execute in a execute commit fashion. They execute with commit and then execute. All of the execution happens post commit, and that creates a restriction in that all of the vector and tensor cannot accept. Right? They've already been committed to execute, and then they execute. So their pipelines can be much deeper and way after commit. It's a little different. And then just like normal, all the instructions, they basically operate on registers local to each of the types of instructions and shared memory. Well, either shared or dedicated to that thread. I'm going to talk about the memory model a little bit. So, as usual, this is pretty normal. The communication between threads just through memory, normal synchronization mechanisms, mutexes and semaphores and such. Memory's coherent between the threads. We have a D-cache. So the D-cache, that is only used though for the scalar side. And the reason for that is that we have a massive volume of vector and tensor data just streaming through. There is no reason to pollute the data cache with all of that data. And it also simplifies things if we just leave the data cache is just for scalar. So that's why we do that. Then we have an L2. Obviously, it backs both of the L1s, the data cache and the I cache. But that also acts as the L1 for the vector side. And on the vector side, software prefetching is used to hide the latency to the L2. And then we have a big TCM for Snapdragon 8 Gen 2. It's 8 megabytes. So this acts as a software managed cache for the vector and the tensor engines. You may ask why? Why are we doing a software managed cache? And there's a few reasons for that. We did that so that we could scale up to very high bandwidths at a large capacity. A very initial reason was actually scatter gather. This did make a very nice path to get very high bandwidth scatter and gather through, because then it was not a bunch of tag. We didn't have to deal with tags like for every single access, and obviously it has a much better predictable performance. There's no misses. So and it's just like the rest of caches, this also has a translation. We use a DMA to go back and forth to transfer to hide the latency into the TCM and to copy. And that's, you could think about that for very high performance software. In the end, software has to really manage all that data flow. Either if you're using caching, it's prefetching, it's hints, all of these things. We decided it's just, you might as well just go to a TCM instead. And then instead of prefetching and hints and all that stuff, just copy. It's still burdensome to the software, so just have the software just do direct copy. It's still data, and they're still moving the data, so it didn't seem like a big downside. So yeah, that's why we've been using a TCM instead of caching. So efficiency. Okay, this will be the fun part. I'm going to talk about how we're getting some of the efficiency we're getting in the Hexagon NPU. So first, let me just talk about locality. So with this giant tensor engine, lots of compute, getting data locality is very key to that. You just can't get that compute unless you can feed that beast. So you got to get the data locality. And I'm going to talk about a few different dimensions of locality. So the really big reason to go with a tensor engine is this ratio is pattern of matrix multiply, and it has a really great property of memory or data versus compute. So if you're talking about a square matrix multiply, you have to read 2n squared worth of data. So that would be the two operands. If we're with ML, that's going to be activations and waits. And you get 2n cubed worth of ops, right? N cubed max. It's a ratio of n to 1. In my opinion, this is the single biggest reason to even think about doing a 2D engine, is this ratio. We chose output stationary. The reason we chose output stationary is it really had to do with the accumulators. So accumulators, they're for fixed point especially, they need to be wider bits, so we don't want to move them, and then they're read and written for when you're doing the accumulate has both a read and a write associated with it. So we end up with the way we do our inference. The accumulators just stay in place, and you go through all of the input channels, all of the filter taps to get your one accumulation right in place, so you don't have to go accumulate with something else. It's already fully there and then ready to be down converted back to memory. Another type of reuse is used on convolutions. So instead, with a convolution, an old school way of doing things was to use this thing called IM to call, where you copy the activations based on the different filter taps. We basically just do all of that in hardware, so there's no data movement there. And effectively, we treat a convolution as kind of like a series of unaligned matrix multiplies. Another big thing is we treat this tensor SIMD just like a vector SIMD, in that the data for our SIMD quantum is contiguous. So this chunk, this hardware tensor chunk, is contiguous in memory. It's not scattered across. We have to go through all this striding and such. And the reason for that was we could maximize our memory bandwidth. It was a lot simpler. And another reason is that it allowed, it's a really good way to allow the software to carve up a tensor into a lot of little chunks. So it is more complex, and we also don't have to worry about this strided memory access that you would normally have like in a raster style tensor. So that's how we're doing that. Okay, floating point versus fixed point, fun topic. Okay, so we have this big beefy hardware, and when you have all that compute capacity, as Bill was showing earlier, the max, big portion of the pie. You really want to make that fundamental multiply add ultra efficient. So this is a little analysis we've done here. You have here on the x-axis, we have accuracy. So it actually uses the same equations you were using earlier, Bill, and basically builds out for any of these data types here, what is optimal scaling, and this is across normal data for the signal, and this is a base 2 signal to noise ratio, shows that MSE like Bill was talking about. So that's the x-axis, is basically accuracy, or signal to noise ratio. And then the y-axis is cost. I will admit this is a spreadsheet model. This is not measured, but this is I'm talking about how we arrived at some of our decisions. This is showing, though, for different exponent widths, what does it look like across different precisions, and this is up to 16 bits total, right? So I'm not showing the data points here, but so that's what this is showing. And interesting thing here is that if you're just looking at maximum accuracy with normal data, at least, it ends up to 2-bit exponent is actually the best if you're talking about just normal data. And then also when you add exponent bits here, it actually, with the same bit width, it's more costly, and that's because you're trading you may get better on the multiply power. The problem is the alignment. The alignment actually screws you up on. You're thinking that, like with FP8, you're going to get better because you get to lower a smaller multiply. Well, no, it actually burns. You get eaten up by the alignment costs. So if you're looking at just cost versus accuracy with normal data, at least, plain old integer looks pretty good. So what I showed earlier, what I showed in those previous lines, those were assuming fixed point accumulation, though. I also went ahead and added in, okay, what about floating point accumulation? And yeah, you can do that. And that actually does kind of equalize out and make it so going to more exponent bits is a little cheaper for a given bit width. But that's because we're the same accumulator, the same type of accumulator. The baseline cost is quite a bit. Oops, let me go back a little bit. The baseline cost, though, is quite a bit higher. And that's because of the alignment costs associated now with accumulation coming back. So this next little chart down here is now with real data. So it was the previous analysis was just statistical data. I have a paper here linked in there. Is an analysis across a variety of networks. This is a comparison between int8 and FP8. And int8, for all of these CNNs, it does look to be better than FP8. And that's because CNNs generally have normal data. Now, transformers are a little different. Transformers, though, you can see here, a little worse. It was significantly worse on PTQ. Okay, sorry. So yeah, I'm sorry. Things are worse with BERT here, but we can recover with quantization-aware training and some other techniques that are shown in this paper you can look at. So we are targeting instead large floating point capacity. large fixed point capacity instead of floating point capacity across a variety of types and they're asymmetric. So we have from 16-bit down to 4-bit weights. I'm gonna have to hurry up here. So this slide is about the efficiency between across different types, and you can see here that there's a quadratic scale across these different bit widths, which instead of just a plain old 2x, and that's because we take advantage of both operands, activations and weights. So I'm gonna have to end here. I'll take your questions.
Okay. All right, take this speaker. Kind of crazy session here. All right, let's start with questions again. And remember, we have the two mics on either side. State your name and affiliation, and let's begin the questions from Slack.
Okay, thank you, Eric. You piqued the attention of a lot of architects in the room when you said that the commit happened before execute, because the questions are all over the place with respect to any issues that show up after you commit, but you haven't completed the execution. So are there any issues with the data-dependent exceptions that would cause a committed thread not to complete? In the execute after commit model for vector and tensor instructions, how does a late error condition like ECC or something be handled? Many more of that. So if you want to talk a little bit more about how you managed to...
So I would say it's like a store exception. So stores happen post-commit as well. They can have an error in the same way, and they would end up being like an imprecise exception. So for the most part, there isn't any of that in these, except for say store. But it's the same problem. Stores are post-commit.
I suppose, but if you have an ECC issue on your load data, you didn't complete the execution of the problem. I think that's where people are going with.
Oh, so on the load side. So on the load side, we also treat an ECC load exception as also imprecise. So we basically leave it as, we boil down to the same cases we have on the store side. It becomes imprecise.
Okay, thank you.
Okay, question over here on the right.
Shrikant from Google. So can you explain the motivation for using threading in the microarchitecture, and can you tell me what kind of threading model it uses? Is it SMT, for instance?
It is SMT. Yeah, I mean, we have all the threads just so we can fill up the compute resources.
Good, thank you.
Okay, another question over here.
Elias from Google. I cannot understand how independent this processor is. Does it need a message from a host processor to start processing? Does it ask for the data to be placed somewhere? Or it just, when it starts execution, it knows how to fetch the data from?
I mean, it would follow just same model as a CPU. So there's an instruction sequence. It's up to software to control that. So it's completely software controlled.
Thank you.
Yeah.
Let's return to Slack.
Yeah, so Andreas Prodromou from NVIDIA was asking, what kind of improvements have you made to the Hexagon IP to support higher math utilization for transformer models? Any updates specifically for the large language model transformer models?
So the large language models, in the end, they are just going to be DDR bound. We have ample compute, so optimizing the compute side of that problem isn't really going to help the large language model because we have to get all the weights in. So so optimizing it would really be about increasing that DDR bandwidth more than anything else.
Okay, nothing to do with the size of the data itself. I mean, you already have a lot of sizes in the model. That also may help?
It's really about DDR bandwidth.
Okay.
The compute, we're end up going to just not utilizing that compute very well because it's about data bandwidth.
Okay.
Let's take one more from Slack if there's any. Do we have another question from Slack?
Oh, I'm sorry. There are so many questions in Slack. Give me a second. Christoph Novak asks, what's the per clock throughput of the Tensor unit? How many?
In the it's 16 kilomac.
Okay.
So 32, 32K ops per cycle.
Okay. This is a straightforward question, straightforward answer. Thank you.
Okay, let's thank our speaker.
Thank you.
Okay, our final talk for this session is Supercharged AI Inference on Modern CPUs, presented by Subutai, Ahmad, and Lawrence Spracklen. Subutai is CEO at Numenta. He's passionate about neuroscience, deep learning, and building intelligent systems. An accomplished technologist, he has been instrumental in driving Numenta's research, technology, and business since 2005. He previously served as VP of Engineering at Yes Video, where he helped grow the company from a 3-person startup to a leader in automated digital media authoring. In 1997, Subutai co-founded ePlanet Interactive, which developed the Intel Play Me2 Cam, the first computer vision product developed for consumers. Dr. Spracklen is a senior technical advisor at Numenta and head of AI at Archify.ai. Lawrence has a decade of experience in developing and delivering AI solutions at scale. He served as CTO and VP of Engineering at several AI startups, including R-Squared, Support Logic, Alpine Data, and IASTI. He also worked at VMware, NVIDIA, and Sun Microsystems, where he led teams focused on hardware architecture, software performance, and scalability. The floor is yours.
Thank you, Grant. So thank you. It's a pleasure to be here. Is this microphone on? Yeah. Can you hear me?
Are you live?
Can you hear me now? No? Thanks. I would like to thank the program committee at Hot Chips for inviting us to present here. So our talk is going to be a little bit different from what you've been hearing so far. At Numenta, we try to think about AI very, very broadly. Now, the core of our presentation is going to focus on transformers and large language models, but we think it's important to look a little bit beyond that and see how AI might evolve and what the impact that might be on hardware architectures. So here's another version of a graph you guys have seen a lot of last few years. As you know, deep learning has had tremendous demand on compute power. In fact, over the last 30 years, there's been over 1 billion times increase in the compute power that's demanded by deep learning. And this has far outstripped the gains that you can achieve just by pure improvement in hardware performance alone. And what this means is that in order to close this gap, we really need to look beyond hardware. We need to look at algorithmic solutions, different ways of optimizing our systems. The discrepancy between the red and blue lines is one of the core reasons why we've seen spiraling costs, complexity in deployment, increase in power usage, and so on. So the question is, where are you going to get these algorithms insights from, and how are you going to go about implementing them on hardware? So at Numenta, we believe that one of the best ways to go about this is to look at the brain, to understand how humans implement these algorithms, and then try to translate that to architecture. So I know a lot of you are already pretty familiar with Numenta, but I'll give you a one-slide summary. We were founded back in 2005 by Jeff Hawkins and Donna Dubinsky. The core mission is at Numenta has been to understand the neocortex, the algorithms in the neocortex in depth. The neocortex is the largest structure of your brain, and then to take those ideas and understandings and apply them to practical AI systems. So we've had 2 decades of deep fundamental neuroscience research that has yielded significant breakthroughs and advances over the last 18 years or so. So Jeff has published a book called The Thousand Brains Theory that I've shown on the bottom right there. We're not going to go into the details of too much here today, but it was one of Bill Gates' top 5 books of 2021. And if you're interested in the details, I encourage you to pick it up and read that. What Numenta is focused on today is to take that understanding, take all of those learnings from neuroscience, and to build a next generation AI platform. We're going to launch that more formally in about a month. And in this platform, we've been able to achieve 1 to 2 orders of magnitude performance improvements for large language models and enable really scalable deployment of these models on CPUs. And we have partnerships with a number of different companies, and we'll focus a little bit on the Intel, what we've done on Intel chips today. So the fundamental question we ask at Numenta always is, how can neuroscience improve AI? This has been a non-trivial task. Neuroscience is incredibly complicated to think through. And we're not going to go into in detail today, but I want to focus on 2 aspects of neuroscience that will be relevant. The first is the neuron itself. As you can see from this video, biological neurons are significantly more complex than the simple linear weighted sum model that we use today. Those complex branching structures called dendrites, they have thousands of connections or synapses on them, but the computation is highly sparse. As few as 10 active connections can actually cause a detection event on these neurons. The second piece I'd like to focus on today is what we call contextual routing. One of the strategies the brain uses is when it has a tremendous network, but when an input comes in, it decides on a per input basis a highly sparse subset of the network that's going to be actually relevant to that particular context and routes information through that subset of the network. So these are just a couple of the strategies that the brain uses to get its incredible energy efficiencies. As you may know, the brain only uses about 20 watts of power for hundreds of billions of neurons. So the question is, how can we map that to hardware architectures? A couple of years ago, we partnered with Xilinx, and we were able to show that in the context of FPGAs, we can get over 2 orders of magnitude improvement in throughput, latency, power efficiencies without any accuracy compromises. And what we've been able to do over the last couple of years is actually take those ideas and apply them to modern CPU architectures. Okay, so I'll let Lawrence talk about that. Oh, while he gets his headset on. Yeah, one of the interesting challenges here is that we have in the brain, there's so many different types of sparsity. It's not just sparse connections. The learning itself is sparse. The activations and the routing is sparse. Of course, the connectivity is sparse. The learning is actually really dynamic in the way it's sparse. So all of those factors actually lead into the efficiencies of the brain. And so hopefully, over time, we'll be able to layer more and more of those algorithms into today's hardware architectures. Okay, Lawrence, you ready?
Yeah, hopefully the mic works now. Oh yeah, I can hear myself. Awesome. Sorry about that. Technical difficulties. Okay, so as Subutai mentioned, sparsity is one of the key ways that the brain uses to deliver its incredible compute efficiency. And we've known for a long time that you can apply sparsity and sparse techniques to artificial neural networks. We can create sparse CNNs, we can create sparse transformers. We can even create extremely sparse models. We can remove over 90% of the weights while delivering equivalent accuracy to the dense model. So the question then becomes, why the hell are we all running dense models in production today? I bet if I was to take a survey, most of the models running out there today are dense, right? So what's going wrong? The problem is that actually extracting sparse performance from sparse models and general purpose processors is hard. If you look at today's CPUs or GPUs, they're really optimized for sort of dense, predictable, dense matmul compute, right? We've got high clock speeds, deep pipelines, wide vector engines. They like predictability. You've got to be able to stage that data in well in advance to keep those engines busy. And sparsity is an anathema to that, right? Sparsity introduces irregularity, right? We've got a couple of sparse weight matrices up on the top of that slide. You've probably seen them all too often for the last few days, and I do apologize for showing more. But essentially, if you have unstructured, it's completely unconstrained. During training or pruning, you just allow the network to decide where it wants to retain its connections, where it wants to retain its weights. And so when we have a packed representation of that, as we see on the bottom with CSR, basically, we're trying to find, we've got a data element. All right, this guy's on row X, column Y. Now let me go and find the activation, pair them up, multiply them, persist them. It's no wonder the performance is horrible, given that's what we're doing. So people have known this, and people have tried to fix it by trying to make sparsity more amenable to general purpose compute today. Things like block sparsity, where we say, all right, you can't have these single elements anymore. They need to occur in blocks. A 4x4 block, an 8x8 block, right? Now we've got some data locality. Now maybe we can get those vector engines going. And we can even introduce additional structure. We can partition it and say, out of this small number of weights, n of them must be non-zero, right? It allows us to basically load balance that compute a lot better across multiple processing engines. And it works to an extent. This is looking at Intel's math kernel library. So this is optimized MATML code. This is running on an AVX512 processor. And basically what we're looking at here is a 1024 by 1024 matrix. And we're looking at unstructured sparsity, CSR, and we're looking at block sparsity, BSR. And we're seeing here that realistically we need to get to 90% sparsity to even break even. Right? I mean, that's a horrifying thing, right? We're doing 1/10 of the useful work, and we're only able to achieve parity with the dense multiply at that point in time. We need to go to 95% sparsity to actually achieve any sort of decent speed up. So with 1/20th of the useful work being done, we can actually achieve maybe about 2x, right? And so, given this situation, it's absolutely apparent why I wouldn't go to all the effort of creating these sparse networks and putting them into production. So this is hot chips. Most of the talks today are about people designing, building, and shipping new hardware. And people have and have done very well at creating domain-specific AI accelerators, hardware that's specifically tuned to running AI networks, sparse AI networks. The problem is that's, a lot of capital commitment, a lot of resource commitment, a long timeline. You've got to build the compilers, you've got to build the ecosystem to support it. So we took a slightly contrarian approach, which was to say, let's assume that the hardware is a given, that the hardware as it exists today is all that we have to play with. What can we do with sparsity? How can we reimagine sparsity to actually improve the performance of sparse networks on existing general purpose processors? And that's what we've been working on, and that's what we succeeded in doing, essentially allowing software to handle the complexity in a way that allows us to get performance benefits with 50% sparsity and scale linearly from there. This technique works equally well on CPUs and GPUs, but we're a small company, so we had to prioritize. And so we went out and spoke to our customers, said CPU first, GPU first. And, oh sorry, did I just blind someone with laser? My apologies. Sorry. Overwhelmingly, people came back and said CPUs first, right? Customers love CPUs. They're easy to use, multi-tenancy is great, IT ops guys love them, they're simple to manage. When we spoke to our dev teams as well, they're like, yeah, AVX programming is super simple compared to sort of hardcore tensor programming. And so basically, we've led with our CPU inference. We initially rolled out an AVX 512 version, right? AVX, yeah, it's vector, but it's still pretty fine grained. You can manipulate those things pretty easily. And then the landscape changed. Intel went from AVX and AVX 512 to AMX. With their Sapphire Rapids release, which I believe was early this year, GA over the summer, they started putting little MATML engines in each of the cores, right? And the performance that you can extract from these MATML engines is way, way, way higher than you can get with AVX 512. And so we needed to adapt our code to actually be able to leverage that. And so some speeds and feeds around the AMX units. So basically they have their own state in the cores for managing, the operands, scratch space, all of that kind of good stuff. It's organized as 8 tiles. Each tile is 16 rows by 64 bytes. And then they have these array of processing elements. Those guys are capable of doing 1024 BF16 ops per cycle. So as I said, that's an incredible amount of compute, a lot more than you get with AVX 512. There is a typo on this slide. I apologize. The sizing of the units of operation is wrong. That should be 16 times 32, not 32 by 32. Incredible amount of performance, all right? Basically handling 16 activation rows per 16 clocks, and if you're doing sort of GPT style models where you've got sort of vector matmul operations going on, even then you're doing one of those in 9 clocks. Obviously, as is always the case, it's critical to hide the load latencies, basically keep these guys fed. One of the cool things about the architecture is you can actually use AVX 512 in parallel with AMX. And so under the hood, while the AMX units are busy, you can actually do, the AMX units output data as FP32. So if you're going to put it back into an AMX unit subsequently, you have to convert down to BF16 again. So that's one of the operations you can do. We also use it for data swizzling and things like that, a lot of the permutations that we need to make our techniques work. And then also, your softmaxes, your GLUs, your layer norms can all be hidden as well. The big problem here is that, again, there's an assumption that's baked into the hardware, and this is being done in so much hardware out there today, that you want to do dense matmuls. And this is really problematic for sparsity, right? Especially for these large matmuls, right? You couldn't really put block sparsity in here. It's too big. A block of that size, your accuracy would be horrible. And so you need to think about novel techniques. And so basically what we've done is we've developed a technology where the complexity of the sparse operation is handled in software, and the AMX unit is completely unaware. It's just running dense matmuls. So given all the hype around generative and transformers, we obviously focused on demonstrating the performance benefits for transformers first. There is so much hype around Gen AI. I mean, Gartner says we're almost peak hype. We're getting there. But still, when we talk to customers, a lot of people think that generative AI is the only game in town now. And so there's a lot of education to sort of say, yeah, it's great, but it's still as relevant today as it ever was, right? It's almost like people haven't realized that BERT's been around for 5 years now, and they could have been solving a lot of these problems 5 years ago. But nevertheless, BERT is actually very cost effective. It can be less error prone. You can achieve higher accuracy. And so it's really non-generative and generative AI. And so we often lead with non-generative solutions like BERT. And so we'll start with some BERT numbers first. This is looking at the performance that we obtain on a Sapphire Rapids using our sparse technology and comparing its aggregate throughput at inference. We're baselining against an AMD Milan. And then we're also looking at the performance we get on a third-gen Intel part, the performance we get running a dense network using AMX on a Sapphire Rapids, and then our solution. And you can see from this that from an inference standpoint, it's about somewhere between 60 and 100x what you could get on a third gen. And even compared to a dense network running on AMX, it's still about 20x. And again, here, all of the networks are optimized Onyx implementations. We're using layer fusion, all the good optimization, so it's not some sort of slow thing running in PyTorch or something like that. Some scaling numbers here. This is looking as we scale the number of clients. It's the 2-socket Sapphire Rapids. You can see that we get linear scaling up to about 48 cores. After that, it plateaus. Number of reasons for the plateaus. This is actually a sort of worst case scenario, if you will. Each of the clients is interacting with its own BERT model, so sort of extreme multi-tenancy, if you will, where, when we're running 48 active clients, there's 48 BERT larges running simultaneously across those 2 sockets. And so basically, we're blowing through the cache. We're putting a lot of pressure on the memory subsystem. The other thing is, as you start to light up those AMX units, you start to get thermal throttling kicking in at some point as well. And then finally, we're running here with an open source inference engine. And it's not 100% clear to me that it's absolutely sort of NUMA aware. And so there could well be incorrect placement that's causing some of this as well. The cool thing to note as well is if you look to NVIDIA's website and see that the numbers that they report for an A100 doing this exact scenario, we've got this situation where the absolute flops that are being delivered by an A100 by NVIDIA, blow everything else out of the water. But the combination of AMX plus smart software actually delivers a better, more performant solution than sort of a brute force MapMol approach to the problem. Switching now to generative, everyone said about generative. I'm sure everyone in the audience is aware how expensive it is, right? I mean, these models are thousands of times larger. The dirty secret, which I don't think many customers know, is this sort of iterative build out. To handle a user query, you run BERT once. For autoregressive decoding, basically we're running it 5, 10, 100, 200 times, right? That's a massive increase in cost right there. And then the context windows, we had BERT was 512, now we're up to potentially 100K. And so it's not 10 times, it's not 100 times, sometimes the cost is 1,000 times higher. And so really, Gen AI has its place, but as I said, I think there does need to be a cautionary tale around that. And also it makes it even more important to leverage software smarts such as this to bring down the computational cost. Here is looking at a GPT-J model running on a Sapphire Rapids. Similar results for Llama, similar results for Falcon. Basically, compared to a 3rd gen Intel part, we're again getting about 65x, and compared to an A100, running the exact benchmark, and I think we're using faster transformers here. We're trying to get the optimal performance out of the A100. It's about a 10x improvement in throughput. I think it was mentioned in one of the previous talks as well, is that you can do a lot of things when you get this kind of performance advantage, right? You can reduce the latency, you can reduce the number of systems you need, you can reduce your compute costs, or you can go after accuracy. Everyone ultimately is computationally constrained, right? You may only be able to run a 3 billion parameter model to meet the latency constraints, to meet the throughput volume, to meet the cost. If we can make these models 5, 10x faster, now you can start to run a 10 billion, a 15 billion, a 20 billion parameter model in the same performance envelope as you were previously able to run a 3 billion parameter model. And so as a result, we're actually shifting the accuracy curve. And so using smart techniques like this, it does allow us ultimately, for any given amount of flops you have at your disposal, to increase the accuracy of your solution. So I'm just going to conclude my components and I'll hand back to my colleague Subutai. AMX, game-changing, I think, but very much focused on dense. A lot of these solutions now are packaging dense mapmols into their cores. We managed to get sparsity to work and an efficient sparse solution to work this time. It's not always going to be the case. If there are any hardware architects in the crowd, it would be fun to talk about ways that we could actually incorporate support for sparsity into these things. I don't think it needs a radical overhaul, right? There's a few tuck-ins to some of the tensor cores out there that can make the world of difference for actually pursuing, efficient sparse solutions on top of general purpose processors. And so, Subutai.
Thanks, Lawrence. Let's see if my microphone working now? Okay, great. So what Lawrence described is just the start of what we're doing. Fundamentally, what we're trying to do at Numenta is take the field of neuroscience and turn it into a technology that we can apply to AI. So I've listed here several different aspects of neuroscience that we've looked at and have theories around. We only talked about a couple of those today. What we're doing at Numenta is taking those neuroscience discoveries, creating an AI platform that's going to accelerate inference dramatically, accelerate the entire model creation process, and eventually lead to completely novel hardware architectures, as our experience with FPGAs has shown. And then there are numerous different application areas. Today we're focusing on NLP, because that's where a lot of the focus is today. But fundamentally, this is a foundational technology that can be applied across the breadth of AI. I mentioned earlier that we have a platform that's coming out very soon. This platform will take these neuroscience discoveries, enable really scalable and secure private deployment of LLMs on your own infrastructure with 10 to 100x scaling improvements purely on CPUs. And this can be applied to a number of different NLP domains. Okay, to summarize, in terms of AI today, a lot of the focus is on deep learning and inference and training. what we found in speaking with customers that inference and training have very different requirements, and Lawrence spoke about some of them. In inference, you really want to have multiple tenant solutions. You want to have asynchronous clients, low latency, ease of programming. These are all really critical issues for inference today. And what we've tried to show is that if you're smart about the algorithms itself, CPUs can actually become an ideal platform for AI inference workloads. As a lot of you know, GPUs are just not available to enterprises for the next year and a half. And what we're showing is that you can get equal or far better performance with a very flexible programming environment on CPUs today. But even beyond that, we think neuroscience really shows us the future of where AI is going to go. The brain shows us how we can build extremely low-power systems that are very highly sparse. The brain dynamically routes information only to where it's needed. The way you get performance improvements is to avoid doing unnecessary computation, not just going things faster and faster. You can actually avoid the unnecessary stuff. And ultimately, training and inference actually have to merge. In humans, there's no such thing as a training phase and an inference phase. All of us are constantly learning with every input. We're making predictions and we're constantly learning. And so the implications for that on architecture are going to be pretty immense. And this one thing alone you can imagine can really bring down the red curve closer to the blue curve. If we can actually avoid constantly retraining our models and have models that actually incrementally learn as they go, this would be a huge benefit to power usage. And eventually, what we'd like to say is that the future of AI is not just about faster and faster matrix multiplications. You really want to enable innovative algorithms and deploy them on hardware. So to do that, it's critical to have a very flexible programming model. And we think modern CPUs with this combination of GPU and CPU-like flexibility illustrate directions that we have to go. So if there are any semiconductor chip companies in the audience, we'd love to partner with you and see how we could take our algorithms and maybe showcase your hardware. We've gotten really good at taking these algorithms and figuring out how to map it to different hardware architectures. If you have any questions or want to contact us about that stuff, please send me an email here. Thank you.
Thank you. Let's begin Q&A by approaching the microphones, and let's start with questions from Slack.
Hang on. Okay, here we go. There was a question about how you chose your comparison points, and the question basically says, why didn't you choose a 64C Milan or even an EPYC Genoa using AVX 512 when you were doing the comparisons? You referenced AMD Milan on slide 12. So just question.
Okay. I can answer that. Yeah. So we absolutely tried. There's a multi-month wait list on Azure to get them, at least there was at the time. So we're a small company. We don't have a bunch of stuff. I thought cloud was compute on demand. I've since learned differently. It's very difficult. I got my first H100 last week. So, yes, the comparison's a little dated, but we do what we can. So it's not sandbagging. It literally is what is available.
Yeah, and the other thing I want to point out is that in terms of AVX 512 and some of these other platforms you mentioned, we actually just released, I think Intel actually just released a very detailed case study that goes into all variations of this. Again, it doesn't have the H100, but it has some of those other variations.
Okay, thank you.
Okay, let's take a question from the right.
Hey, Natalia from Cerebras. Thanks for a great talk. I have two questions. The first one is, can you comment on the level of sparsity that you used for benchmarks of BERT and GPT models? And the second, both of the benchmarks has been using extremely short context windows. So if BERT was, 64, GPT was 32 for 32, they're not realistic. Why that and how you perform on long contexts?
Yeah, so the sparsity level and kind of the impact of context length and stuff. So we try a variety of different sparsity lengths. The ones that we showed were sort of 1 in 16. I think that was the basis for, but we look at a variety of them. We can get really high accuracy with 1 in 16, but and actually even better accuracies with, obviously with 1 in 8 and so on. And in terms of sequence length does have a big impact on speed. For BERT models, there's almost a quadratic impact on some of the layers. So all of the the comparisons go down as well as our numbers go down, but we still maintain a very healthy difference between the two. So yes, the relative difference does shrink as you increase context length, but we're still significantly faster.
Can I comment how much faster if I use the standard context with like GPT model with the context of 2K?
Well, with BERT, I think we've gone up to about 512 context lengths with the GPT models. Now we're looking at Falcon and Llama 2, and we don't have those comparisons today, so that'll be...
Yeah. I think just to add as well, right, I mean, essentially, if you're going to push context length, you want to pair it with something that's doing some potentially sparse attention and things like this, right? Because otherwise it's known that basically that will dominate cost. And so our technique is complementary to a lot of those other, long-form or big bird style models that are out there too.
Let's take another microphone question. Go ahead.
Elias Google, thank you for the talk. So these algorithms you talked about, they can be applied on like any kind of CPUs, on a cell phone or a data center. It's a generic solution, or it's right now limited to some applications?
Yeah, it can be applied to a wide variety of architectures. We're really encouraged by the NPU combinations in some of these mobile platforms and stuff, so we'd love to work with companies and see how we can port our stuff to that. But we think it should be very doable.
Let's take one more Slack question, then one quick microphone question.
Okay, this is from Savarish Ravikumar from Waymo. He's got a bit of a comment that says, have you actually managed to find a way to make sparse matmuls work well with AMX AVX 512? That's his comment. But the question is, can you talk a bit more about what kind of sparsity is assumed?
Yeah, so we're not disclosing a lot of the technical details of how we do it. We have published papers on our FPGA implementation where we showed how we could take dynamic activation sparsity, dynamic routing of information, as well as weight sparsity, and how the combination of those two can lead to multiplicative things. So some of those ideas are in our current implementations, but for various reasons, we're not disclosing the actual details of our CPU implementation.
Okay, questions in the channel, so if you can maybe pop a reference to that paper in there as an answer, that'd be great.
Yeah.
And quickly,
Hi, Andreas Prodromo, NVIDIA. You showed a chart with throughput with asynchronous clients running BERT large. And I'm wondering if you can explain why throughput increases with more clients and then it just stops. How you mentioned that something along the lines of each client runs a BERT instance. Did I catch that correctly?
So it's the aggregate performance, it's not the per client performance, right? So it's the cumulative. So you'd expect, like, as you scale the number of active clients, right, on a multi-core. So basically, in that scenario, we're not using all of the threads. I mean, that's the beauty of CPUs, right? You can right-size it, right? So basically, we're using one core per client. You've got 48, 96 cores. And so basically, we can handle up to 96 concurrent connections before we even have to start, context switching or multi-threaded. So basically, it's the aggregate. And we're saying, you get sort of linear scaling with aggregate up to about 48 cores. And then, funkiness kicks in as you get power throttling and, you blow out your caches.
Yeah. We actually think it should be higher than the numbers we showed. We still have some optimization.
Are you doing any batching or pipeline?
So that was batch size 1.
Batch size 1.
Yeah. The NVIDIA comparison was batch size 8, I think, from the NVIDIA website. But we were doing batch size 1. No need to have batches with CPUs.
Okay. Thank you. Let's thank our speakers.
Cool.